Imperfect multicollinearity arises when two or more regressors are very highly correlated, but they don't contain the same information. When there is imperfect multicollinearity, the OS estimates might still be unbiased, but they are no longer imprecise, which means the estimated standard errors for the betas are no longer the smallest of all possible standard errors for the betas. Let me show you what this means using two examples. This example is based on simulated results. In this simulated world, y is given by 2x plus u, a random error term. There are 100 data points in this simulated sample. U follows a normal distribution, and the variable x and z follows a standard normal distribution. The correlation coefficient between x and z is very high at 0.99, which means that the variable x and z are very highly correlated. Notice that in this example, y is only dependent on x. Y is not dependent on z. And therefore, when you regress y on x, as shown in column 1, the estimated beta for x is 2.25, which is fairly close to the true beta in the population model. If you conduct a t-test for the x variable, you will see that 2.25 divided by 0.3 is very high. That means the x variable is statistically significant. And in this case, we see that the estimate for x is both unbiased, meaning the expected value for beta is equal to the true population beta, and consistent, meaning the standard error for x is very small. Now, if we include additional regressor z into the model, notice that z is not relevant in explaining the variation in y. But nevertheless, if we include z into the regression model, then what happens is that the estimate for beta for x changes significantly. It goes down from 2.25 to 1.55. And additionally, the estimated standard error for beta is for x exploded. It goes from 0.3 to 2.54. And as a result, the t-test for x variable shows that this variable is no longer statistically significant. What happens to the estimate for z is that the standard error for z is also very high. And if you run a t-test for z variable, you will see that this variable is also statistically insignificant. Now, by including additional variable z into the regression, you will see that the adjusted R-square decreases from 0.33 in the first model to 0.32 in the second model. And this is because you're including additional variable z, which is irrelevant in explaining the variation in y in the model. So you get penalized by having a smaller adjusted R-square. If this is the case, the fix is very straightforward. You just need to drop the additional variable z from the regression model. And afterwards, the estimated beta for x becomes unbiased and consistent again. What is more ambiguous is the second situation. In the second model, I modified the previous model by letting x depend on both x and letting y depend on both x and z. If this is the case, when you regress y on x, you will see that the estimated beta for x is 0.72, which is very different from the true beta for x, which is 2 in the population model. This happens because we're missing z in the regression model. In other words, our estimated coefficient for x is suffering from omitted variable bias, which we'll elaborate in the next lecture. Okay, well, you see, how about now I include additional variable z in the model and rerun the regression. And this is what happens, as shown in column 2. The standard error for both x and z in the second model are very high, such that the t-tests, a simple t-test for x and z shows that both variables are no longer statistically significant. And when this happens, the second models are also not a plausible model to use. But now your hands are tied. You cannot use the first model because in the first model, your coefficient for x suffers from omitted variable bias. But similarly, you cannot use the second model because none of the coefficients in the second model are statistically significant. Well, in this case, your hands are tied. There's no easy fix that you can do to render the coefficients unbiased and consistent again. This problem is prevalent in macroeconomic research when you need to include multiple macroeconomic indicators that are highly correlated in the same regression model, such as unemployment and GDP growth rate. Now, to recap, you can diagnose the imperfect multicollinearity problem by adding additional variable sequentially, one variable at a time, step by step, to see how the regression changes. This way, you get to see when the problem is introduced, and you know exactly which variable is causing the problem. However, in the first situation, as explained in the first model, you can fix the problem by dropping the additional variable that is causing the problem. But in the second situation, as shown in this example, there is not much you can do to fix the problem. Now, let's pause this video to do in-class exercises number 5 and number 6.